In this video, I'm going to demonstrate how to create a plot of means with error bars, confidence intervals, that are adjusted to reflect the fact that in a within subjects design, the data are correlated, and consequently, the analysis is more powerful. And specifically in this example, I'm going to use the plants versus cleanliness study, where I wanted to look at the interaction effect. And in the foundation section of the chapter, I looked at the plot of means with the regular unadjusted 95% confidence intervals. And now I want to adjust them. And the key to making the adjustment in an efficient way is to use this formula here. Pooled adjusted standard deviation equals the square root of the mean square error. And you can get this mean square error for the analysis from the within subjects ANOVA, which I've already done and I won't redo here. It's in this big table, tests of within subjects effects. And in this case, I want to report the error bars for all four means that were reported. They're actually reported here, but also lower down when you get down to the confidence intervals. Here we go, plants and tidy with the confidence intervals here. I've reported that chart already. These are unadjusted, not accurate with respect to a direct comparison from the factorial within subjects ANOVA. And so what I need to do is I need to adjust the standard deviations, which will allow me to calculate accurate confidence intervals, at least in relation to the factorial ANOVA. So here's the mean square error that I need, because it's really the interaction effect that I'm going to be presenting in terms of trying to interpret the result. And the mean square error is 0.973. And to get the adjusted pooled average standard deviation, you simply need to square root that value. So 0.973 square rooted gives 0.986, and that value is what is going to be used to adjust the raw data. And once I have the raw data, I can actually calculate the confidence intervals again in a fairly efficient way. And so here I've got the raw data. I need to convert these into z-scores, and then I need to multiply them by the adjusted standard deviation in order to get data that reflect the adjustment for the correlation across conditions. Now, I'm assuming that you have already followed me do this in the paired sample t-test chapter, as well as the one-way within subjects ANOVA. So I'm assuming that you're already familiar with this procedure because I've covered it several times already. So first I need to get the z-scores, so descriptive statistics, and I'm going to put all four levels. I'm going to get the z-scores, and I'm also going to keep the mean and the standard deviation, just because I'm going to need that again in a few minutes, just for the purposes of comparison. So I've got the data converted into standardized scores, and I know that the standard deviation was 0.973 square rooted, which gives 0.986. So I need to convert these data to have the means that they have, but adjusted standard deviations. So you can see the standard deviations here in raw score form are this big. I need to get them each this big, 0.986. They're all going to be reduced quite substantially to reflect the fact that the data are correlated across conditions. So let me do that for the first variable, compute variable, plants, tidy, adjusted, and I need to put the mean in for that, which is 6.91, at least a 2 decimal place, 6.91, and then I'm going to plus the value of the z-scores times the adjusted standard deviation, which is 0.986. 0.986. And OK. And I'm going to do that for each of the variables. So now I need another one, which is plants untidy. And the mean for that one corresponds to 4.42. 4.42, and I need to get rid of this variable because I need to put in the z-scores for that, and I'm multiplying it by the 0.986. They all get the same standard deviation because the interaction analysis is based on a pooled error term. And keep going, transform, compute, and no plants tidy, adjusted, which has a mean of 5.93, And I'll change that z-score. No plants tidy. And click OK. And the last one, whoops. No plants untidy. It's got to mean a 3.96. And change those z-scores. And multiply by the standard deviation, the common pooled adjusted standard deviation. Now I can analyze those data just to make sure that the means are the same, because I don't want to adjust the means. I just want to adjust the standard deviation. So here we've got the mean 6.91, 4.42, 5.93, 3.96, and here are all the adjusted standard deviations. Now I can get the confidence intervals for each of these pretty easily, like the adjusted confidence intervals, by putting in my adjusted variables in the Explorer utility and clicking on statistics and descriptives with confidence intervals for the mean of 95%. And I just want the statistics. Click OK. And here I get the mean plus the confidence interval. These are the adjusted confidence intervals because I'm looking at the adjusted data. So 6.91 with quite a narrow confidence interval now. Now again, these means and confidence intervals are a reflection of the interaction effect analysis. They're not the true standard deviations or confidence intervals. That's based on the raw data. I'm making this adjustment because I'm interpreting them in the context of the interaction. So now that I've got the means and adjusted confidence intervals, I can create adjusted data file in order to create the high-low chart. So what I need to change are really just these values here from my original plants tidy error bar chart data file. So I get rid of those and input the confidence intervals that I've got. So let's see. We've got 6.78, 6.78 for the lower bound, and 7.03 for the upper bound. Now I can keep scrolling to get the next ones for plants untidy adjusted. So plants, yes, there are plants, and it's untidy, so 4.297 and 4.542. 5.93 is the mean for that condition. And now I need to input the lower and upper bounds for those. 5.807 and 6.05. And here we've got the last one, 3.83, 3.83, and 4.08. So now I've got this adjusted data set that I should be saving. But once you've saved your adjusted data with another data file name, you can rerun the analysis and just go through Graphs Chart Builder. And you do have to remove the old values if you are doing this as a supplementary analysis, because it looks like SPSS remembers the values that you input here. So take them out and then put the, even though it's the same variables and it's a new data file, just re-put the values into the boxes as required. So lower bound into low value and upper bound into high value. And I want to put plants as my x-axis and cleanliness as my panel. So I'm just redoing this based on the same process I did for the adjusted values. So columns, panel variable, make sure that's selected. I'm assuming you've watched the video for the unadjusted creation of the plot of the means. And then click on OK. And then you get a new chart that can be compared against the means that were presented based on the unadjusted confidence intervals, which is this. And you can see that the error bars are a bit smaller. That'll make it a little bit more obviously comparable. I'm going to clean things up, get rid of the fill, get rid of the border, and importantly, get the scale on the same level. I'm also going to change this. The y-axis label, which should be comfort, and then change this number format 1 and text style to 10 and bold. And let's change the scale from 3.5 to 7.5 and 1 major increments. And we've got the new chart, which, let's actually change the size of this as well to, I think it was 3.5 from memory. And we have very slightly smaller error bars in comparison to the original chart made over here. So you can see that for no plants in the untidy office, the 95% confidence intervals range from here to here. And then in the adjusted confidence intervals, look how much narrower they are. And that reflects the fact that there's a correlation across conditions. And I want these means and confidence intervals to reflect the power of a within subjects design, which reduces error associated with respect to testing the null hypothesis of equal differences between the conditions. And so in this case here, as I've discussed in the previous description of the unadjusted data, the magnitude of the difference here is larger than the magnitude of the difference here, and that is testimony to the statistically significant interaction. And in this case, I've actually got the adjusted confidence intervals.